So we were talking about how to get the dead load moments for different, how the section from the girder design, you need the girder by itself and the girder as a composite. And we calculated the dead load moments for different. Now we want to apply the live load. And as I said earlier, the live load is the HL93. It could be in a single lane or two lanes loaded, and one case will control your design. So when we say the lane moment, you put one lane, the HL93, and placing the truck in the maximum moment position, then you get a moment. That moment, which is the lane moment, has to be distributed to the girders. That's why the new LRFD, the difference between that and what was done before it was how many wheel loads will be distributed to each girder. Here, so there's a difference between the distribution, uh, but the total moment per girder should be comparable between LRFD and LFD. However, the way distribution factors are interpreted, they're not the same. So here we are taking one lane moment and we are distributing it to the girders, or we take two lane moments. When we put two trucks side by side, we find the total moment, and then we distribute that moment into each girder, the interior girder and the exterior girder. So now the opening part of the live load is to know how do you distribute that live load. For that, you would have to use, as I said earlier, the distribution factors. And those equations that were developed by Imson and Associates are applicable. They have some limitation also, because depends on, they didn't, in the finite element modeling, they didn't cover all the cases that were about, you might see, especially for very high skew, for example. So they used, what they did, they used right angle bridges, they modeled them, and then they adjusted the results for the skew angle. If you have any skew, you have multiplied by a certain factor. So those are, if you notice here, those are the requirement. Width of the deck is constant, number of girders, basically more than 4. In this case, it's equal to 6, what we had. So you have a minimum. AASHTO allows you a minimum of 4 girders because of, especially for the fractional critical, you can't go lower than 3 girders. 4 girders, sorry. Okay, so now these are the tables. Your bridge has to be one of those categories. If it's a precast concrete, girder, or if it's a steel girder, you have different types of bridges. And, the equations will be done accordingly. So our case, we start by applying the applicable equation in this case, which is for 2-lane. Most of the time, 2-lane loaded will govern your design, depending on the type. And this is the K sub G that I was referring to, which is depend on the moment of inertia of the girder alone and the area of the girder. And EG is the distance between the slab, between the CG of the slab all the way to CG of the girder. So you would find that first. You would find KG value. Okay, you plug it back here. You find distribution factor. In this case, if we apply 2-lane, the equations for 2-lane, you will get, excuse me, about 0.74, meaning about almost 75% of that lane moment is going into the interior girder. Okay, this was what it's saying. And if you look at for the shear, there are different factors for the shear, and we listed the table where the excuse me, for the shear factors are listed. You would use that. And for 2-lane loaded, again, you have about 88% of the total lane shear is carried by the interior girder. Okay. So some might argue that, oh, this is a lot, but that's based on these distribution factor. If the distribution factor equations do not apply to your case, you cannot use them because your case doesn't fit into the category, then you might have to do your own analysis or the lever rule, whatever other method that is in the code. But they would allow you to do your own refined analysis also. We've done, actually in the RIME app, this was one of the, for deflection, instead of using, because those factors are a little bit conservative. Maybe when you use finite element, you get the exact distribution, and that can help you when you do that. However, you have to remember, when you do use your own analysis, okay, you still have to multiply the single lane by 1.2, which is the multiple presence factor. The good thing about these distribution factors, that they are in them already the multiple presence. So when you get the distribution factor, you multiply it by the lane moment, you get the girder moment. You don't have to multiply by the multiple presence factor. It's already included in this equation. But if you use your own finite element, for example, so you're coming with your own distribution factors, then the multiple presence factors have to be applied on top of that, okay? Sometimes people would forget that. Say, oh, the finite element is giving me much less distribution. Well, because you're not multiplying by the multiple presence factors that are already embedded in these equations.
Professor?
Yes.
I noticed on this example, if you can go to a couple of slides back, on page, I guess 78. 78, there you go. So here, what differences would be if you have a fanned arrangement of girders? In other words, like a fanned arrangement, not parallel fanned.
Yeah. So this happens.
Do you take average S? What's the deal?
Yeah. So, for example, if you have a 3-lane bridge coming into a 2-lane, and then it's usually what they do, they put a variable spacing, right? That's what I think you're referring to, isn't that? In this case, right?
Yes. In other words, it's not a constant width of the deck, and also the spacings are not. It's in a fanned arrangement. In other words, one end is one spacing, the other end is the other spacing. So how does that work on these formulas? I think you are muted, Professor. Professor, you're muted. Professor,
right. How it gets muted, I think. Anyway, I think, Ali, you are revealing one of my exam questions. So usually I give that as an exam. And so here, usually that case might be when you have a 3-lane bridge coming into a 2-lane bridge and then a flyover. And so what you do is you try to start, maybe you're starting with 12 feet girder spacing, and then at the end of the girder, you might end up with 9 feet, and then you might go from there even to about 6 feet, and then you go. So that variable spacing, so it depends, people use, for example, can use the average of that. However, if you're doing it in a way where the maximum moment is, then the distribution has to follow the spacing where the truck moment would be. That's how, academically speaking, I resolved that, and we solved it in one of those questions. You can take the larger spacing, and so in other words, if the truck moment is applied in the middle, and the average spacing, let's say between 9 and 12 is let's say, I would say 10 feet or 11 feet, then you would take that with that moment, because that distribution is happening at that location where the distribution is basically going through that girder spacing if you take a transverse cross section. However, for shear, if you're doing it on one of the supports, then you might have to use, for shear, you might have to use the spacing at the ends rather than in the middle. So in a way, to get a factual number, you might go with the most conservative and you would use that. But that would be sometimes a too conservative estimate. So for shear, I would use the girder spacing where you are placing the truck, basically, because the distribution is following the transverse moment, where the moment or the shear is being considered.
Okay, thank you.
You're welcome. Sorry, I think I went too far ahead. So here's the live load moments. So remember we derived an expression. Mouse is here. We derived an expression for the moment from a truck as a function of x. So you would apply that, and you would find out what is the maximum moment position, In many cases, the maximum moment position is not going to be in the middle. You're given this truck. What I usually do is, for my students, I show them that how to find the maximum moment position for end truck. You would find the resultant, and you would place the center line of the beam at half a distance between the axle closest to the resultant. So in other words, here you have 32, 32, 8. The resultant will be 72 here, about 4.6 feet apart. And then you would place that center line of the beam at the middle distance between the heavy axle closest to the resultant, the distance between them. Then this would be about 2.3 feet from the center line. So about 2 feet, 2.3 feet from the center line, from the middle span, would be your maximum moment, right? But the uniform load has the maximum moment in the middle. So as a compromise, you just place, the way they did it here is they place that truck right in the middle. Okay, that doesn't mean it gives you the maximum moment, but more or less together, it's easier to add them up together. If you want to be more exact, the WL squared over 8 happens in the middle. Okay, you can add that moment that comes from the truck being also the heavy axle being in the middle and in the middle span. And that more or less very, very close. The dynamic allowance, we are going to use 33% in this case. It's a girder, so we applied that. And then the factored live load plus impact times the distribution factor. And here is the lane moment, okay? You will get about 2,244. So that's the live load moment coming from the, two-lane loaded, this. Now, this here, I'm a little bit ahead of myself here. So this is at mid-span. So this is one section. And if you recall, because there's interaction at every section of the span, there's the moment and the shear, they're one increasing and one decreasing. There will be a point where the shear is critical. And if the 10-10 is draped, in other words, if it's harped and it goes, some of them go, towards the top of the girder, some of them continue straight, then the center of the steel is going to go up. That means when it's inclined, the pre-stressing force itself will resist the shear. So you will need to know where is the critical shear depth, and that is, it's 5.68, okay, and this, when we go to the section of the shear, you would know where is that. So you would need to find that ahead of time. Where are the critical section you're gonna design your beam at? One of them is more important, is the mid-span, where the maximum moment is, and the critical shear, where the shear has to be considered. That 5.68, we will see, it depends on the, what we call DV and the in the shear, which is related to the cotangent theta, and the modified compression field theory. So let's accept this as is now. And then when we go to the shear, we will explain how you would do that. So basically, before you do this work, you would have to know where is the critical shear, okay? And then you take your section based on the profile of your tendon, because the beam has to be checked for all sections along the length, okay? Not only at the maximum moment position. There might be other locations, depending on how the pre-stressing force and how the tendon profile is, it might be still more critical than mid-span. But most of the likely, mid-span will be the most critical. And again, the impact, we realize the critical shear is usually a distance from the center line or the face of the support, whichever you want to measure it. Here, it's 5.68, and I believe in the calculation, we did it from the face of the support also, if you know what the width of the support is. Oh, what happened here? So this is if I take that and I apply this, equation, it's basically, you have 3, P1, P2, P3. These are equations available in the LRFD manual, available in the LRFD manual. You can use them, we provided them. And then you can get the moment of the truck at that particular section, okay? And, and then you put the lane also in the same way. then the maximum moment and impact using the same approach here, you did it in here, and you get 480 kip feet. So that's the moment, live load moment at the maximum, at the critical shear, section. And you also find it from the lane, here, okay, same way. And so this is the total, the moment from both of them. I mean, the shear, sorry, from both of them need to be calculated. Next one is, now you found out what is at each section, you have to do that. You found out the moment, you found out the shear, after you distributed everything, so you have the shear per girder, for the girder and the moment. Now you have to find out what is the load combination, because you have dead load from before, you have live load, and based on that, okay, you would start, the stages of how you're gonna, when you are designing, first you're gonna put the girder by itself before you put the deck on top. So there will be some moments there and shear due to its own self-weight, right? Then on top of that, you put the forms and you cast the slab, but still, the weight of the slab, when the slab is still in plastic concrete, does not contribute anything to the girder. So you have to figure out that the girder has to have enough strength to carry the weight of the slab by itself, the dead load. Once the slab is cast and it's solid with the deck, composite with the deck, now you can rely on the deck to resist some of the stresses. Then it becomes composite with the girder. Then you have to use the composite girder, geometric properties. So this is here, when you do the service one, all the loads acting are non-composite. So you would add them up. This is, if I go back, I believe those are the different components, and, maybe I don't, so here's the dead load, I think here. So yeah, this is mainly dead load, okay? So this is the lane, and this is the composite girder, okay? The weight, when the total weight is, you're adding the weight of the slab on top of it. I mean, the weight of the, I don't know if this 192 is there, but let me see. So this, the live load is 2244. This is the one here. And 275, we got to go back to the dead load, I believe, earlier. Where's the load here? So you would get, depending on the X, I think we calculated them. Let's see. We're not putting the dead load separate, but we would have to. What's that? Anyway, so this is the first service one. These are for the moment at midspan. These are the moment acting on the non-composite girder and the composite girder. You do the same thing for service 3. However, the live load factor here is 0.8. The reason is 0.8. I explained that because we are using we will be using the losses, not the refined losses, but without the elastic gain. So you would have to stick to 0.8, okay? And you find out the moment, same as service 1. Here, at service 3, you have to add, the load factor here was 1, but here you have to reduce that by 0.8. So now you can see that the moment is reduced for service 3 is less. And once you get, and strength, you have the ultimate, you factor them, the ultimate loads, you factor them according to dead load, and then you have 1.5 times the asphalt, okay? I wish we wrote down, I think we should have wrote down each one what it is so that you could follow. Maybe we can add that and do that. So this is the total factored moment, and this is the total factored shear, and this is at the moment at the shear. So, it's obviously less than that, but there is interaction between the two. And then this is, you end up with a summary of all at different sections. This is at the transfer point. This is at, 0.8, 0.45 L, okay? And this is at midspan. So those are different location, and we found out the moments and shears, and you end up, for different limit state. If you tabulate them like that, I think it will be better because then you are checking every limit state by itself, so you need to have those values. For service 3, we're only checking it at midspan because this is what's going to be more critical than other location. It goes because this is about cracking, in the middle, the maximum moment. With this one here, so at this stage, you have the dead load. We don't know what is the pre-stressing. So what people have done here, they have used equations, the stress, what we call stress equality equation, meaning you could find out the stress at any point on top of the girder or bottom of the girder based on this equation, okay, which is the pure compression from the pre-stressing applied axial force divided by the area. That's the total compression that you're applying. Then you have the stress from the pre-stressing itself, the eccentricity times the force will give you the moment that the pre-stressing is opposing the dead load, okay? And that will create tension in the top and compression in the bottom, at initial. And I here, so this is the tension at initial, the stress in the tension, which is mainly on the top, when we have camber. And then the minimum here represents the dead load mainly, okay? This is the notation that is used not in AASHTO, but in the book by Professor Naaman, who did the work. And then you can stress, this is the stress and tension. You have to make sure it's larger than the allowable, okay, or at least within the allowable. In this case, he puts it larger because he uses for tension, he uses negative. The other book, like book by now, he uses tension positive and compression negative, which I think as a concrete, we use compression as positive because concrete can take compression, but tension is a bad thing in concrete, so we put no tension on it. So if you build these equations, and so you have 4 of them, right? We have tension at initial, service at initial, tension at service, and compression at service. Okay, so tension, compression at initial, tension, compression at service. And those are the 4 equations. Okay, there might be more, but those are the dominant ones. The 4, we call them inequality equation because sometimes the stress has to be larger than the tension or less than the tension. Sometimes have to be larger than a minimum compression stress, right? So you have that. And you can write them this way. Traditionally, you can come up, you notice here is you don't know the eccentricity, right? Because you don't know how many tendons you're going to be using. You don't know how they're going to be distributed. And you don't know the area of steel. You don't know how many tendons you're going to use. So some books, they do what we call trial and error, meaning that you could try number of tendons 32 from experience, come up with a E0, the eccentricity, and then check your stress equation. That can take a long time, and it's not really, it's not going to satisfy. It might satisfy 2 conditions, but it might violate the other conditions. So sizing the number of tendons based on the tension at service, most of the time it works because this is what your main bottleneck is, that you don't want to have it crack or have tension at service. So that could be your bottleneck. But sometimes if you put too much pre-stressing in the beginning, you might be cracking it in tension at the beginning. So, so one way of doing it, and this is a diagram that has been developed before Professor Naaman, but in his book, he highlighted this. And I teach this in my course because it's an easier way and a quick way to find out the minimum pre-stressing force. That's your objective, to use as minimum number of tendons as possible and to put them at the maximum eccentricity as possible. So in this stance, if you use, in addition to this equation, if you use all 4 equations, okay, they become like a linear dynamic problem where you can solve these 4 equations for a domain where all 4 are satisfied. And that's why it's called the feasibility domain, okay? I think those were done before, but he really elaborated on it. And if we do that, if we, we write the equation, we have all this Fi here, the initial pre-stressing force is unknown, eccentricity is unknown. And Fi is the initial pre-stressing force. F is the effective, or if you apply the losses, NFI, if you know how much losses, you assume 20% losses, then you can use, 0.2 times that will give you the Fi. So here you have 4 equations, but you have only 2 unknowns, which is the pre-stressing force and the eccentricity. So the 4 equations with 2 unknowns, you can get many solutions. And that's why we need to be in a feasibility domain, okay? And to be able to do that, if you write the equations, so this looks like an equation of a straight line. So it's like y equal a, x plus b, y equal b plus ax. So x here is 1 over Fi, okay, 1 over the pre-stressing force. So that's an equation of 4 lines that they will intersect. And if you write the quantities correctly, you can see that you end up, you have the pink line here, or a purple line, the red line, the green line, and the blue line. Okay, so those, they have a point of intersection. If this is the area, any solution inside this domain will give you a good result. It will satisfy all 4 equations, right? Because this will be less than this, above the blue line, lower than the red line, above than the green line. So that means if I hatch this area here, okay, that's the visible solution. And that makes it very quick. So you write an Excel sheet here, and I usually give this in my class. And, and then you have another condition, 5th condition. It's sometimes the eccentricity, to get an optimum one, you might get this point. This point is giving you the minimum, the absolute minimum force. So intersection of the red line and the blue line is giving you the minimum pre-stressing force. But that's not practical, because then the eccentricity is outside. It's not practical. It's going to be outside the section, or maybe very low in the section. It doesn't fit. So you need to have, what is the minimum practical eccentricity? And that's what we're saying here. Okay, I don't want my center of steel to go below 34.6 inches in this case. And that's the yellow line. So that means this is the yellow line, and the red line is the point of the minimum pre-stressing force. And that's what you start with, right? So that means from here, I get that the number of tendons, number of strands is going to be a minimum of 35. I'm saying let's use 36. And that's what the example is done in a different way. If you read the example from Federal Highway, and I encourage everyone to download it, they do what they call trial and error. And when we do that, it might be, if you don't have the experience for the type of girder, for the type of length, you might be doing it more than a couple of times to be able to converge into a number. I think this one here is much more practical. And now that everybody uses a spreadsheet, it makes sense for us to use that. So that's what we call the feasibility domain. And then the answer is done, and you are using 36 inches. Okay. So after that, now we know we had the number of strands that we're gonna use. And there are, according to the pattern that you're gonna, we do start from the bottom up. We try to fill all the layer on the bottom because we wanna maximize the eccentricity. Spacing between the tendons everywhere is 2 inches. So you have, because these are the standard, distribution that the pre-stressing plants has. When you wanna order these girders, this is what they do. They start putting them, they have these holes spread into equal 2 inches cover. So you don't want to try to change that because that's not possible. So at mid-span, you want to put them as low as possible. So you start here by full number of tendons, and then you start reducing the number as you go to keep a 2 inches cover. And so here the CG is maximum. However, at the end of the girder, when you are distributing the number of tendons, if you keep all the tendons straight and the bottom, then you are creating a pre-stressing moment at the end. But there is no resisting moment at that point. The moment there, dead load or live load moment is zero. So you end up inducing more stress at the support than needed. So what you need to do is you need to make sure the eccentricity of the tendons at the support becomes close to zero. I mean, you might not be able to harp all your tendons up, but so at the end, you can see some of those tendons that are here, we move them like maybe at, 0.4 L or 0.45 L, I mean, even more, you start going up with those gradually. And then you end up getting them all the way to the top of the girder. Then the pre-stressing steel has a center somewhere in the CG of the shape. That means the eccentric moment due to the eccentricity of the pre-stressing is going to be diminished there. And you don't need to resist that moment, right? So this is the main objective of doing that, of trying to, deviate the tendon and harp them. So the configuration, once you have that, and you are putting the depression points at 0.4 or 5 L. This is where, at 47.5 feet from the center line of the bearing of the girder. And, so you would know what is the CG at midspan. So, as I said, here you are having the tendons at 2 inches. So you count them, you count the distance. You have to find the CG of the pre-stressing. So you can find E0 that you need, the eccentricity that you need. Same thing, you can do that on the other side. So here is the pattern we're using. Sorry. So here we're putting 4 strands, okay, at 8 inches, okay, distance from the bottom. And I'm putting 8 strands at distance 6 inches from the bottom. And I'm putting 12 and 12, 2 layers, one at 4 inches and one at 2 inches from the bottom, right? And here the drape tendons, I am putting 2, 2, 2, at 68, 66, 64, 62. And the straight, the ones that I keep straight, so you are taking only those up and keeping all the rest here, keeping them straight. Okay, so that will allow you to find the CG of your. So this is the CG here, okay, and at the end of the girder also. Okay, are there any questions up to this point?
Hani, just one thing. I think you are trying to use your mouse to show something, but I think your mouse is not showing. Better to have the pen to.
Oh, okay. All right. Thank you. I thought it's in my showing. Okay.
And Wasim is, here to.
Okay. So I needed to take a break, if you don't mind. I think it would be better. And if there's any questions, please ask. I'll be here all the time. But to help me out, a couple of my colleagues and students are here. Wasim, Adi, and Sirab. They prepared this example in more details. So I would like to ask Adi and Wasim to take over the explanation of this example. So maybe you wanna start presenting on your side. Yeah, I'll stop sharing so you guys can share.
Sure. I'll share it, and Wasim, you tell me where to.
Okay.
Okay, so here we are having as Dr. Nassif mentioned, the center of gravity is found mainly at midspan, at the support and at the depression point, because these are critical points. Also, the center of gravity can be found at the transfer point. Now, what's meant by the transfer point is from the end of the girder, it's going to take some distance for the strands to stress, similar to the development length in reinforced concrete, which is roughly equal to 60 dB. And we can calculate the center of gravity there. It's not of significance, but this is what the example shows. Also, it has to be calculated, and this is important, at the critical location for shear. In the next session, there will be an explanation how to find that critical section for shear. Okay, next slide, Jacob. Okay, now the pre-stress losses. As Dr. Nassif mentioned in the previous slides, when the feasibility domain was used to calculate the number of strands, the percentage losses was assumed to be equal to a certain percentage. It was assumed to be 21%. Now we are calculating the losses. Now, we assumed it to find the number of strands. Now we want to have this number of strands that we computed to find the losses. Now, what happens if we get losses that are different from the assumptions? We have to start over and recalculate the number of strands until we get a convergence. Now, the pre-stress losses, there are many ways to compute the pre-stress losses, but this is the simplest way presented by Ashto. The total losses are the sum of the immediate losses by elastic shortening of the member when it is compressed, to be added to the long-term losses from shrinkage and creep and relaxation of steel. Next slide. Okay, so the elastic shortening, as mentioned, it occurs because the compression force would shorten the whole member, and because the whole member shortens, in turn, the strands will be shortened, and thus there will be some losses. Now, how is it calculated? There are two ways. It's EP over ECI. EP is the modulus of elasticity of the strands divided by the modulus of elasticity of concrete initial. CI means at transfer. So we get EC at transfer, not after 28 days. It depends on the day of transfer, multiplied by FCGP. Now, what's FCGP? It's the concrete stress at the center of gravity, at the location of the center of gravity of strands. So it's not in the strands. It's at their position, but it's in concrete. Now there is a way, like instead of calculating it this way, there is another formula to calculate FPS, which is you can see it, the ratio of APS, FBT, whatever. It uses the moment of inertia, the EM, which is at midspan, AG, the area of the section, and the other parameters that you can see. Now, ECI is computed from FCI, from the concrete strength, using this formula. Now, for concrete strength more than 10 KSI, there is another equation presented by Ashto. We don't need it here because our strength is less than 10 KSI. Okay, so yeah, the next one is the time-dependent losses. As mentioned, it's the shrinkage losses, the first term, and the creep losses, the second term, and the relaxation losses. Each one has its own formula. These parameters, gamma H and gamma ST, are dependent on the first one on the relative humidity, which we can get like based on the site. It was 75% in our example, and gamma ST, it depends on the concrete strength at the time of transfer. FPI, now FPI is the pre-stressing steel prior to transfer. It's called FPJ, the jacking force, and delta FPR is the relaxation loss. It depends on the type of strands used. For low relaxation strands, it's 2.5 KSI. It's different for high relaxation strands or other types of strands. So, okay. Adding up the immediate losses and the long-term losses, we get the total losses. And this value has to be divided by the initial pre-stress, FPJ, the jacking force. And this is the one which has to be compared to the assumed loss in the beginning when we used it in the feasibility domain. If it's equal, if it's the same, then we don't need to recompute our calculations, and it is. So if you remember, it was 0.79. 0.79 is 1 minus this. So we're good. Our assumption was correct. And it's not always the case that we get it from the first time. We need to do trial and error, but it's easy with the use of a spreadsheet. Now, the effective pre-stress is the initial pre-stress minus the total losses. And from that, we can calculate the force, and we get 80 kips. Now, there is a restriction on FPE. It shouldn't be higher than 0.8 FPY, sorry, the yield stress of strands, which worked here. Okay, next. All right. Now having the number of strands, having the percentage losses, we need to check. We need to check our stresses. Now, you might argue that we already checked the stresses in the beginning, and that's true, but that's based on an assumption. Now that we have everything, we need to recheck to make sure that it works and at every section and at every loading. So, for instance, we calculate the stresses in the top and the bottom part of the girder. Now, first, bear in mind that we have the girder itself, and we have the composite section, the girder and slab, and we need to check both. Now, checking only the girder, we need to check the stresses in the girder due to its load, its own load, self-weight. And we can get the top and bottom by simply dividing by ST and SB. Now, what's ST and SB? As you remember from mechanics of materials, the sigma equals my over I. Now, SB is the inertia, the moment of inertia divided by Y bottom. And same for ST, it's I over YT. We have these values in a previous table. So we compute them. Now, our assumption is plus for compression and negative for tension. It doesn't matter as long as you know what you are doing, but you need to be consistent all the way because we are adding up later the stresses to check if they are less than the allowable stresses specified by AASHTO. Now we can calculate the girder dead load at release and after and final. Now what's the difference? The difference is that you know that it's a 1 foot, half a foot outward from either support are the girder ends. So at release, the girder wasn't placed on its support, so it was on the ground. So when it cambers, it rests on its ends. So it's 106 feet. Now later, when it's placed on the piers or abutments or whatever, it's 105. This is more critical, of course, the higher span, but it's not very different. Now then we calculate the stresses in the girder due to the load of the deck. Now the deck is placed on the girder, so it's going to induce stresses, top and bottom. And we have the moment of the dead load. Of course, each girder has its holds a certain distance width of the slab, so based on the effective width mentioned before. We have FT and FB, F top and F bottom, and similarly we find FT and FB due to the non-composite dead load, which is the topping, and later we can find the barriers and the future wearing surface, their values added. But these, the bottom one, composite dead load, barriers, and future wearing surface, you can see that the values of ST and FB are different. Now, why? Because these are placed above the deck. So the deck would hold these parts, the barriers and the future wearing surface. So these values are for the composite section. Okay, the next slide. Also, similarly, we can find due to the live load, the FTG, we mean by FTG is F-top girder, FTD, F-top deck. Now, the live load is held by the composite section, not by the girder only. So the values are different from those of the self-weight. Okay. Then we calculate the concrete stresses at release, the time of release. So we use FPI. PI is the initial force. It's 1,020 kips. It's the same formula that we use always. It's the force over area plus M over My over I. PE is the moment. The force multiplied by the eccentricity is the moment. We get at the bottom part the stresses, and at the top part, and then we calculate it after losses. After losses, we use FPE. This should be E, the bottom one, and we would get the stresses. The next slide. Is there any slide in between? Okay, no. All right. Now we will add the stresses later. Okay, so again, now we want to calculate the concrete stresses in girder at surface limit state. We already calculated the stresses at each and every loading. Now we add them up like this and that. If you refer to the previous slides, we had these values. We add them up and we check them against the allowable stress. Now, the compressive stress at service shouldn't exceed 65% of F prime CI. And we check it and it works. As for the tensile stress, it shouldn't exceed, this is a negative value, this expression, minus 0.0948 square root of F prime CI, and it barely passed. The next one. Similarly, we use different load combinations, service 1 and service 3, and we check them the same way. We just add up the stresses at the same fiber, whether they were positive or negative. We add them up. If in tension, it should be less than a certain value or greater than a certain value, and same in compression. And we do that for the girder and for the slab. You can see that we are adding up the different values under surface 1, compressive strain on top of girder. We're adding up the different values of stress that we calculated before. And they are checked against the limiting stress. The limiting stresses are they are presented in AASHTO table 5.923 2B1 and 2A1. So it depends, either at service or at transfer. There are tables for each one. The next slide. Okay, same here. We add them up and we check them. We check them against the limit. Now there is a term here, FFW. It's for the composite section. It would be equal 1 if the span to distance ratio, thickness ratio is less than 15. Okay, this is another check. Okay, for the composite section, and these are in the deck because we already checked for the girder. Now we need to check in the deck. We have the stresses computed before, so we check them against the limit. They are the same, but make sure to check them against the F prime of the deck itself because it's different from that of the girder. Okay. Now, after having all our checks working, we go to the strength limit state. Now, you might ask, like, what happens if one of the checks doesn't work? We have so many options to do. We can change the eccentricity at a certain point where it doesn't work because you know that we are checking it at several points. We're checking it at the ends, we're checking it at the depression point, we're checking it at mid-span. So whenever it doesn't work, if it's off by a large value, you might need to change something. We can change. We can do so many things. We can change the pre-stressing force, change it a little bit in some strands or not. So there are many solutions, and it's easy to make it work. Now, after having the stresses checked at service, we need to design at strength limit state. Now, having the same number of tendons, these tendons are used. We have their properties. They are used to compute the strength of the section at the critical section. Now, how do we do it? Dr. Nassif mentioned that when he was describing the procedure. We find C, the depth of the neutral axis. Of course, this is for the composite section, because that's not a transfer that's at the end of the life. So if it happens and it reaches the nominal capacity, the bridge would virtually collapse. So this is for using the composite section. We find C, we have everything. APS is for the pre-stressing steel. Now AS and FY, these are not included. If you noticed, they were not included in any equation at surface. You can't see them; they are not there. At surface, we only check the concrete section and the pre-stressing steel. So these would work at ultimate, and this would help if the section didn't reach the desired capacity. We can add up more reinforcement, and it doesn't alter our behavior at surface. So we can play with the compression and tension steel so as to get the ultimate strength if it was not attained by the pre-stressing only. And they have their advantages too. They can control cracking, they can control deflection. I'm talking about the reinforcement, whether the top and or the compression or the tension. Now we have this 0.85 that you see in the denominator. It's now alpha 1. It would be like less than 0.85 if we have high concrete strength, but it's not our case here. Now the value of K is found. The value of K that you see in this equation is found using the properties of the strands that we have, and dP is calculated from the top part of the slab to the center of gravity at the critical section, which is the midspan. We have all the parameters. We can find C. We need to check if C is in the flange or not. Now the flange is the slab. Our flange is the slab. Otherwise, we would have it would be in T section behavior. Then we would need to use a different equation. Here, instead of B, we need to use BW and whatever. It changes a little bit. Next slide. Okay. After finding C, we find the depth of the compression block based on the value of beta, which is dependent on F prime C. And after getting A, we will use it in the nominal moment capacity. But before we need to find the stress at ultimate, the highest stress attained in the strands at the ultimate state. It's using this formula, and then we compute Mn based on that. Now, this is assuming that we don't have any reinforcement. If we have any reinforcement, we just add to this term As Fy d minus A over 2. We might need to check, of course, if reinforcement has yielded or not. And then after having Mn, the nominal moment capacity, we find the resistance moment, which is equal to Mn in our case for flexure. And it has to be compared to M ultimate, or the required moment. Of course, it has to be higher. And as I mentioned, if it's not higher, we can just add some reinforcement if it's not off by too much. Otherwise, we need to change our design. Next slide. Okay, so we need also to check the maximum reinforcement by dividing C over DE. Now DE is the average depth of strands and reinforcement, so they need to be included. If we have any reinforcement, it needs to be included in the value of DE. We don't have any here, so it's just DP. It has to be less than 42, and it's almost always the case. It doesn't govern. Also, M resistance has to be checked against M crack or 1.33 M ultimate. M ultimate is the required moment based on our loads. Now, previously in the previous versions, it was 1.2 M crack, and M crack had a different expression than this. But now the new AASHTO defines mcrack as following. It's dependent on values of gamma, whether it is segmental or not, bonded or unbonded, and the value of gamma 3 is 1 for pre-stressing steel, and it's less than 1 if we have any reinforcement. So these need to be checked. FR is the modulus of rupture. It has a new expression now in AASHTO 0.24 F prime C, the square root, of course. And we have other expressions. We have FCPE, SC, and SNC. They are defined in the next slide. FCPE is just like the one that we use in the elastic shortening equation. It's the compressive strength in concrete due to the effective pre-stress only. They are defined. It's easy to find them. This is the non-composite dead load moment, so you don't include the weight of slab. And SC and SBCG, they are the composite section modulus and non-composite section modulus. So one uses only the girder, the other includes the slab. We just plug in everything. It's straightforward, and we check our resistance moment. It has to be higher than the minimum, which is the case. Next slide. Okay, this one we didn't check yet. If you remember, we mentioned concrete stresses. We check the concrete stresses at surface, which is after the application of the topping and the parapets and the live loads. Now we need to check at release. We don't want our concrete to crack when we are pre-stressing, when we are releasing the force from the tendons to the girder. So we check it for the girder only, of course, because when we release, we don't have the slab placed yet. So it's just the same way we do it, but be careful what to use, what ST and what SB to use. Now they're gonna be the girder ones. They're checked at the top and at the bottom. There is no contribution for the moment, for the dead load moment at the ends. It only contributes because, you know, it's 0 at the support and simply supported beams. So it might be critical, the support location, especially in tension. And that's why this is one of the reasons that we use the draping, because there is no load to counteract the tensile stresses in the top part of the girder. Next slide. Again, these are other checks. We just add them up. At midspan, there are two effects: the tendons themselves and the dead load moment. We check the concrete strength in compression not to exceed 65% of the transfer strength stress, and the top to be higher than this. Just the same way. Next slide. Okay, so another check, which is just the same procedure. We're not gonna spend too much time on that. It's at release at the depression point. Now, you might argue, why do we need to check at release if we already checked at midspan and at support? Well, you know that at the depression point, the dead load moment is less. So the counteracting to the camber is less. So it might be critical at a different location than at midspan. So that need to be checked because we don't want cracks at the top too, neither at the top nor at the bottom. So they are checked there. We make sure to have the value of the moment there at that position, which is different from the WS²/8, which we used to have at midspan. Okay, next slide. It just goes the same way, top and bottom. Next slide. Okay. This concludes the flexural design. It's time for a break, Jacob?
Yes. We need to have some break now for about, I believe, yes.
Yeah, thank you, Wasim and Jacob. Should we take any questions before the break?
Yes, any questions?
I think we're a little bit behind, right?
Yeah, we're about 20 minutes behind.
Okay. Right.
I believe after we finish, per schedule, we finish this shared design provision first, and then have a break, and then go over the shared design examples. But maybe you can have a break now for 5 minutes, and then we can do both.
Do the break for 10 minutes. I think let's keep the schedule. We can probably try to make it up, and next day, if we don't finish everything in this today, we can continue some of this. And I think the shear shouldn't take that long.
Okay, then maybe we can just keep going on this session, shared design provision. I think
let's take 10 minutes break, Checo, please.
Okay, sure.
I think everybody needs a break.
Okay, so we'll come back at 2:40 for session 6.
I'm sorry, but was there a break scheduled now, or
No, after another session for 35 minutes for shared design provision.
Oh, okay.
We have a 10-minute break.
All right. So if you don't mind, then let's start with this one. I'll go ahead. Let me share my screen here.
Yes, it'll be slide 108, session 6.
Yeah, I got it. Can you see my slides?
Yes.
Okay, so thanks to Wasim, I think he went through the calculations of how to check the stresses for the allowables and compare them to the allowable stresses in flexure. Now we have to talk a little bit about shear part, because the shear part is very involved in this approach in AASHTO, and it's based on the modified compression field theory. So before I will delegate that probably to Adi and Daniel that did the example, but before that, I'd like to give you an overview of what this theory or this is approach, the modified compression field theory, basically is about. And initially, the old code was based on a very simple shear approach, which meant that the concrete and the steel, together they carry the ultimate shear. So basically, the capacity was equal to VC, which is the amount of shear carried by the concrete alone, by the plain concrete, plus the part carried by the shear stirrups that you have to provide, which is VS. And that was based on the truss model, which assumed that the shear is maximum at 45 degrees, and then anything on the shear at 45 degrees can be carried by the stirrups, which are intercepting those cracks, and then the interlock and the aggregate interlock at the crack will have some resistance, and those were a model, but it wasn't a very rational model. It was based on what has been observed and years of testing since the 50s of shear. And it worked very well. It was conservative. However, the modified compression field theory came and changed that by saying that, well, wait a minute, when we're testing, the crack in the concrete is not always at 45 degrees. And because of the presence of the reinforcement and the other factors, the strain compatibility, we got the angle of inclination of that crack is about 20 to about 30 degrees. It doesn't really go up to about 45 degrees. So this is where I think Professor Collins at Toronto started doing the basic research on that part. And he came first with the compression field theory. And in that one, he said, well, if I have a shear strain and if I have a tension strain in the other direction, this strain should be able to be, it should fail according to something like Mohr circle criteria, where you have the ultimate, the principal strains, the failure strain should be a combination between the shear strain and the compression along the strut and the shear strain. And he assumed that strut is between the cracks that will form, as you see in this picture. Let me use the pen here. So here, there's a strut. So you have the strain in this direction. But in this direction, he didn't really assume that there's a crack here. Therefore, there is no strain in that direction. This was the initial parameter. And because of that, and he was able to find the strain at different levels, okay? And he was, saying that, okay, I have a vertical shear coming from the applied shear, but but I will also have this one here, a V, which is basically, going along that, and that because of the angle theta, I can find out this resultant here, which is, he called it VU cotangent theta. So that was his basic, approach, and then he said, okay, before cracking, I would have a strain in this direction and a strain in this direction, and I'm assuming theta to be 45 degrees, and the maximum shear stress, and I can, using this element, I can, if you want to have a failure criteria like in Moore's circle, and I can predict what the maximum stresses should be, and I'm okay. However, when the crack forms, then the modified compression field theory is not gonna be, it doesn't work anymore, because when this this is is not zero anymore. I mean, it's not, they're not equal. This is, so you have they have difference, and because of many factors, he worked on getting that relationship. So he used what we call compatibility of strain and the rationality of it to try to basically come up with that theory. How did he do that? Well, he assumed that there are some cracks and there are some rebars going in different direction. That's why his theory does not only use the stirrup, he uses also some longitudinal reinforcement at different levels, as you can see here. And he proposes that to resist shear, especially in deep beam, his theory is very, very good and very applicable for deep beam, because the other approach for VC and VS fails completely. It doesn't really predict good results. His approach is the right way to go. So what he did, he took some concrete panels and he put some rebars in them, like you say, the square rebars, and he tried to put that shear panel, he calls it, and he applied loads, shear loads in the 4 directions, as you see it here. So he applied shear, and so the only place, University of Toronto and University of Houston have that kind of approach, okay? So he did many, many tests, and all the tests, he measured what is the angle theta and what is the strain epsilon 1 and the strain epsilon 2. And he tried to fit those into the compatibility of the strain. And he said, okay, if I look at what the stress between the cracks, I can find out that the rebars here should be resisting the shear with this mechanism, which is F1 in this way, and then you have the resistance to that, to crack it, is the shear reinforcement. And he was able to add to that, because of the interlock, which the previous approach has determined that, yeah, it is there is some friction, some interlock, which is VCI. He added that also to his equation, and he was able to derive a more rational model on how failure will take place. And he did not prescribe that theta, the angle here, is going to be 45 degrees. Whatever that might be, that's part of the unknowns. And he was able to derive, so this is the VCI, he assumed that there is a certain crack width, the aggregate interlock, there will be some shear resistance there. He used the same thing. And he was able to apply this equation. I'm going to spare you how did he do it, because it's a very interesting and work. It was published in the early 80s, actually. And so he did different panels, and he was able to produce a model that can relate the resistance to shear, basically the cracking, to the angle of where the crack forms. And depending on how much reinforcement you put in, that angle will change. But it was never, in his calculation, it was never close to 45 degrees. So if you look at this, so he looked at equilibrium. From equilibrium, you have to internal forces, this is the applied shear, has to be equal to the internal forces, okay? And he used the average, stresses, okay? And he calculated the stresses at the cracks here, before it cracks, what they are going to be. And then he applied the compatibility of the strain that, in epsilon x and epsilon z, they have to have a certain relationship together. And he derived that, and then he find out from this compatibility what is the relationship between the strain, the stress, and the strain within the panel. And he was able to evaluate also the shear at the crack, what we call VCI. So given all of that, the background work, he was able to come up with a design approach, an iterative approach using their program, which is but that program, because it had to integrate, over the section. There's a distribution of strain, let's say, over the section. And in the design, he used the average. He used the value here. But sometimes the strain distribution, the strain is negative, and that location might be like this, and it becomes like a negative. That's why in the early stages, they were getting negative strain when they do use his original method. And the negative strain, it shouldn't be a negative strain. You should get a positive strain, because otherwise it doesn't mean anything. So he realized that when you integrate, you get a better value, but you don't integrate using the program. So in 2000, I believe it started in 1998, it was pointed out. And in 2005, he made the final correction to that. He gave a small correction in 1998, but then he revised in 2006, 2007, the revision was revised, and it's been the same ever since. And I think in the shear design, I'm going to ask Adi to take it over from here. And in that example, you will see how you can, when you get a negative strain, and that, the longitudinal average strain, when it's negative, how do you adjust your equation?